Welcome, everyone. We are extremely excited, actually, to be here at PromCon and talk about the new version of Remote Write. And I have to admit, in the context of distributed systems, I have some kind of strange weakness or respect towards designing network protocols and APIs. And I would love to learn if you share the sentiment, but for me, designing network protocols, especially for high volume data and open source, and in open source, it poses a lot of interesting questions, right? For example, like how to make this API, both extensible but also stable. How to make them flexible and powerful, but also like simple, efficient, and consistent. And plus, it takes years to adopt those protocols and really get feedback, proper feedback on what you did. So yeah, it's challenging. And then you have to think about the usual network, problems or distributed system challenges like consistency and availability. So for those reasons, I really like to sometimes study how other protocols work and how they were created. And while I, help a little bit with the design of the remote read, the streaming one, and the streaming mode, and we both help in the remote write protocol, next version of it. It is only when I was preparing this talk, I kind of like look on the big picture of the remote write protocol history, and I found useful learnings. So I want to share that with you, and it might give us a little bit of perspective. So let's begin. So it's hard to imagine, Prometheus without those remote storage interfaces, right? Literally from the beginning of the Prometheus, the developers like Julius, like 11 years ago, issue number 10, were thinking about how Prometheus can integrate with other storage solutions. And back then I found mentions about InfluxDB and OpenTSDB in particular. And such need of this remote storage integration shouldn't come as a surprise, right? Prometheus, by design, it's a single node, and it doesn't have any replication or clustering, so those comes handy. So this is why the younger protocol, Remote Read, was introduced, so any client can, ask for some historical raw metric samples in Prometheus format. For example, it was initially used to enable PromQL through Prometheus against metrics stored in different databases. I think it was OpenTSDB as the first thing. It wasn't long until the read API was also exposed on Prometheus itself, right? Allowing the long-term storage solution integrations like Thanos or project like Thanos to effectively query Prometheus for raw metrics. And for proxies like Proxy, I don't know if you remember Proxy, a really cool proxy that transparently deduplicate, and hide HA kind of Prometheus setups as a single endpoint. However, probably the most nowadays used protocol, remote integration in Prometheus, is the older remote write protocol, right? It allows any client to send metrics, samples in Prometheus format from one place to another, typically live streaming fresh data to centralized long-term storage. And similar to read, Prometheus also supports receiving this format and this protocol, the remote write request, so you can import the metrics from other systems. Now, in May this year, Prometheus released a new remote write 2.0 version. So in the next 18 minutes or so, I would love you to learn why Remote Write 2.0 was even created, what it enables, and how we improved efficiency on the whale while adding more features to the protocol and more data, and how you can use it and adopt it in your organizations. But first, short introduction. I have Alex with me.
Yeah, so hi, I'm Alex. I work at Grafana Labs, based in London. For many years before that, I worked at IBM on a network management product. Yeah, it's a very long time, 20+ years, and ability to work on open source software was limited there. They're good in some respects, so I wanted to escape. I wanted to contribute back to open source with Usebit. So I escaped, and I escaped to Grafana Labs. And at Grafana, I get to work on a bunch of things, including some proxies that help ingest data from other products like Graphite, Influx, OTel, Datadog, and get those into Prometheus-compatible databases. And also I get to work on, contribute to Prometheus and the OTel collector as well, which is cool. In my spare time, I am mostly a taxi for my 14-year-old daughter, going to cricket or football or something else, but I still manage to play a couple of games of five-a-side every week to keep myself going.
Amazing. My name is Bartłomiej Płotka, but it's short Bartek. I work at Google. I'm tech lead for a Google cloud managed service for Prometheus. I love open source. I'm maintaining Prometheus, Client Golang, Thanos, and lots of other Go libraries. I'm active in the CNCF. I also wrote a book called Efficient Go with Rayleigh. And in my free time, I started recently doing some adventure motorcycling, which is not ending always well, as you can see. But that's why we call it adventure, right? And that's why I love it. So Remote Write has a new version, and let's dive why this happened, and how is the second version helping Prometheus end users. To answer that, it's worth to get, again, back in time a bit, and almost exactly 8 years ago, Prometheus merged an MVP of the Remote Write protocol leveraging gRPC framework. The protocol was extremely simple and generic. It was generally a stateless proto request with unstructured labels and corresponding samples sent in order. Nothing more than that. Later, the gRPC framework dependency was removed as the HTTP2 transfer protocol, and gRPC itself was just released a year ago, so many cloud providers didn't support the traffic, the gRPC traffic. Plus, Remote Write semantics, being stateless and so simple, wasn't really benefiting the, unique HTTP2 and gRPC features like multiplexing or streaming. It looks like the simplification was actually a good bet, because organically through years, Remote Write got pretty impressive adoption. And it allowed people to integrate with various solutions, various monitoring solutions, analytic solutions, vendors, and tools. It enabled new long-term storage solutions to be created from scratch, like Cortex, Thanos, Mimir, and so. It kind of started mini-industry with those cloud-managed Prometheus services as well, popping everywhere, allowing you to integrate with your existing setups. Overall, it's fair to say that it became an important open-source standard. And all of this with a single proto, no official specification, no version, pure organic growth, right? It eventually was kind of ridiculous. So a year ago, thanks to Tom Wilkie's work, actually, we released the official Remote Write 1.0 spec in the RFC format, as we should from the beginning. It outlined important protocol semantics beyond the proto format, like retries, compatibility, and so on. And this was really essential to even start talking about improving something, right? The point is that 1.0 Remote Write we use nowadays is kind of exactly the same as it was 8 years ago. And it's both amazing and scary. It's impressive that it didn't require any major changes and allow amazing stability of the protocol, but also scary because ecosystem evolved and a lot of things kind of improved, and it will be useful to add new features, new data. So the second point to realize, which is super important as well, is that 8 years ago, Prometheus team decided to keep both PromQL language and Remote Write protocols, or Remote Read as well, as close as possible to the Prometheus storage data model. We could pick exposition data model. We could pick some other replication, format of another database. But no, we kept this close to the Prometheus storage data model. And this allowed the least amount of overhead when using, those protocols with Prometheus. So super seamless integration. But to me, I also see this as a consequence. This situation kind of forced remote storages to adapt a little bit organically, and we were able to spread this, for better or worse, a simpler, more flexible schemaless Prometheus, patterns to the wider ecosystems and projects and users. However, as you might have noticed, Prometheus storage constantly evolves, right? Expanding beyond the original capabilities. As a result, we have some gap in between Prometheus storage model right now, or what we plan to work on, versus the remote storage interfaces. For example, Prometheus team designed native histograms that give us more efficient, flexible, accurate and structured histograms. And this is for both exponential and classic histograms or custom bucketing. So essentially, we're able to replace classic histograms eventually. And then for some time, we have exemplars, which allow metrics to link to certain resources like traces. Then we have metadata, right, where now we are able to quickly access the helps, like type, description, sorry, that's help type and unit of the metric, and actually we plan to add more stuff. And all of this is incredibly useful to integrate with more type remote storage solutions, as well as PromQL auto-completion. Then we have created timestamp to improve accuracy of rates, but also to, for those short living time series. And finally, the UTF-8 for compatibility with other metric solutions. And all of those were valid reasons to look for the improvement here, to look for the maybe another version, which would enable remote write storages to really leverage what we already store in Prometheus. Now, of course, Prometheus team wasn't just lazy or forgetting about this protocol. In fact, if you go to the proto format of 1.0 right now in Prometheus codebase, you will see a lot of experimental fields that allow some of those features already in a hidden way, unofficial way. This was super useful for development and experimentations on those potential improvements that we did today, or like that we did in May. And this unofficial version is already used by Cortex, by Thanos, Mimir, and other solutions. So we already gather amazing feedback and data on what works, what didn't. For example, like this initial experimental remote write, it was supporting metadata in a specific way, in a stateful way, where the metadata was sent in different requests. And we learned that there are some problems with that around scalability of senders and receivers. So that was a useful insight, among others. So with enough motivation, around a year ago, the ideas for the next remote write version started floating around. So first, we listed the requirements, right? And you know the drill, like generally doubling down on that decision from 8 years ago on sticking to the Prometheus storage model. That was a good bet, and we don't want to break that. Then the ease of use and adoption, right? Since we have Remote Write 1.0 adopted already in various places, it will be really epic if we could just use another protobuf message, and that's it. So upgradability of the whole solution is a key. Then, of course, before committing to any new version or features, it was very healthy to step back and see on alternatives, so big picture on potential ideas as well to consider. So I want to give you like a quick overview of what we consider. For example, we could bring gRPC or make the protocol stateful. The protocol statefulness, it promises a lot of bandwidth reduction for the first kind of like point, network bandwidth reduction. But as our experiments with metadata shown, it is actually sometimes problematic especially on receivers, scalability of receivers, because you have to maintain that state somewhere. If we want to keep the protocol stateless, though, then would using gRPC, for example, streaming, give us enough improvement to justify this another dependency that will make upgradability much worse? Probably not. Plus, we found other ways to reduce bandwidth with this novel string interning that Alex will explain later. So we could make things simpler here. Then, of course, OpenTelemetry OTLP is the new aspiring protocol, right? To standardize transfer of all types of telemetry, be it metrics, logs, traces, and profiles. Unfortunately, OTLP is currently deviating from Prometheus storage model a lot. And while we work on those compatibilities and improvements, as you could see in the previous talk, there are still some gaps that we didn't even chat about, like, for example, mandatory created timestamp for every counter, structure summaries, and then, we kind of like already discussed that, but resource attributes. And all of those will take time to kind of like bring this gap forward and like improve this. But yeah, then trying to kind of like use OTLP as the next version of kind of remote write kind of like brings this upgradability story, to down very much. So we want to really, like highlight the upgradability here and ease of adoption. Now, integrating with OpenTelemetry is on our roadmap anyway, right? So the work for POC of experimental OTLP export is already on feature brand, and we're working on this in some, of course, limited OTLP export in limited fashion because we cannot support everything. But it's still kind of like, yeah, it's in progress. Plus, funny enough, the fact that we release Remote Write 2.0 now brought some certain features forward in the storage, right? So it will actually make, thanks to Remote Write 2.0, it will make it easier to integrate with OTLP in the future. Finally, the arrow format is something we consider as well. It's this in-memory format that promises zero copy reads and CMD compatibility for data processing. It's a new hot thing in the CNCF. Many observability solutions kind of looking around to integrate that, including a new version of OpenTelemetry OTLP. There is an arrow version of that, stateful arrow version. And from those experiments, actually, it was clear that it introduces new complexities. So again, like for upgradability, it's not ideal. But moreover, to fully benefit from RO system, RO format, your processing and storage format ideally is also in RO kind of compatible columnar storage format, right? So we are not there yet, but there are experimentations in open source to kind of like play with it. So we might want to check out those in the future. But right now, this doesn't immediately fit our use cases. So no for now. So with all of this decided on bringing Remote Write 2.0 without those considerations, yeah, we have 2.0 now, and I think it's pretty epic. So Alex, do you want to share what happened next?
Yeah, sure, I can do that. So a lot of the initial impetus came from a Grafana Labs hackathon project by Callum Stein. He used the time to investigate the possible efficiency gains of applying stringing and turning to the Remote Write protocol. This showed great promise, and the work picked up momentum and other interested parties. We started a Slack channel on the CNCF Slack and iterated from there, adding a fortnightly call and to keep on top of things. We used the Prometheus proposal repo, I don't know if anyone's seen that, to help document what we decided to in the end, but also more importantly, what we decided not to do and why. Similarly, the spec was created as a PR in the Prometheus docs repo, and it was open to anyone, and it was a truly collaborative effort, with people giving their input and feedback via calls, PRs, and comments on the various repositories. We were hugely reliant on a selection of significant features contributed to by others that we'll mention later in this talk. So, what does Remote Write 2.0 enable us to do, or enable you to do? One item we looked at was the issue of partial writes. It's been a bit of a thorny issue for a while. The previous iteration of the protocol relied on a single coarse HTTP status code to reflect success or failure of a remote write payload, and exactly what success meant wasn't quite completely clear. The definitions around writes, partial writes and success have now been more clearly defined, and headers are now included to detail exactly what elements, exemplars, samples, histograms, and how many of each were successfully written. This allows the sending client to detect problems and determine whether resubmission is valid and increase reliability because of this error detection. We also added native structures within the protocol for many of the recently added features. So native histograms, created timestamp, all the ones that Bartek talked about earlier. It's also UTF-8 aware. As we saw before, Remote Write 1.0 had no official support for classic histograms. Experimental code had been added, but histograms were often munged into a number of separate series, which could cause problems if all the series were not delivered at the same time. By adding native support for these features in Remote Write 2.0, we solved many of these transactionality issues. This work also allowed us to create a clearer delineation between the protocols for remote read and for remote write. Another problem concerned metadata, the units and help text and types and things. There were various problems here. It was only populated at scrape time, so upon restart, the cache would be empty until the next scrape, until it was scraped again. This caused problems if existing data needed to be sent onwards by remote write. The excellent work by Pascalis and others to store metadata in the write-ahead log was a vital prerequisite for fixing this problem. The remote write system no longer needs to rely on a cache, as it can be read from all the required data can be read from the WAL. We also took the opportunity to move metadata from a per metric family name model to a per series model. That also fixed a few odd situations that could lead to data inconsistencies. But wait, if we're adding all of these new features, aren't we supposed to be making it better? Aren't we making things bigger and slower by doing this? Kind of yes. However, one of the key goals of Remote Write 2.0 was a reduction in payload size. Sending fewer bytes is always a good thing. At the top, we can see a set of metrics with a bunch of label value pairs, and we can see the considerable amount of duplication there. So we use string interning to deduplicate them. The process creates a symbol table of the unique strings and then refers to those strings with the index into that table. The string interning was applied to all strings in the Remote Write 2.0 protocol, not just the metric labels and values, but other strings in the exemplar labels and values and the help and unit strings in the metadata. There's a lot of duplication there. But why did we opt for string interning? Aren't there other ways to minimize the data? And so during the initial investigations, many different approaches were considered for a more efficient communication protocol. Could different compression systems provide increased savings? There are plenty of trade-offs here. Better compression systems often have higher CPU costs or memory costs or something. But ultimately, the biggest win we found was focusing on reducing the payload size through string interning, which can save networking, ingress, and egress costs. And then these smaller payloads take much less CPU time to compress and decompress. reducing overall CPU usage for both sender and receiver. There is also a nice side effect of reducing the number of Alex on marshalling and unmarshalling, which can help with garbage collection, churn, and fragmentation of memory. So we still use Snappy to compress the final result, but a more efficient data structure can lead to better overall compression. Knowing and optimizing the structure of your data prior to compression is the key. The million-dollar question, though, is how much did this save us? With Remote Write 2.0, we spent a lot of time benchmarking various scenarios, including various scrape data sets, Kubernetes clusters, synthetic data sets made with Avalanche, etc., various queue configs and larger batch sizes, and more. And what we saw surprised even us. The following graphs show 3 different measurements: message bytes on the wire, serialization CPU time, and the bytes allocated during the serialization process. And that helps contribute to the contributions to the garbage collection churn. It is important to note that in all 3 of these measures, lower is better. So, and then we show this for 3 different batch sizes, how many samples in each payload: 200, 2,000, which is the default, and a really large setup of 10,000. We hope this covers a wide range of likely implementation and usage scenarios. We do see a slight increase in payload sizes with the default batch size, well, small and default batch size, which is expected as we've got the overhead of the extra metadata that we're sending with every series in Remote Write 2.0. However, with 2.0, we'd see a healthy decrease in CPU time during the serialization process and a considerable decrease in the allocation of bytes during this process. Looking good so far, but a fairer comparison will be to compare 2.0 to 1.0 with all the features such as exemplars and native histograms. We now see considerable reductions in all 3 measures. Remember, lower is better in each of these. But at all batch size tested, small, default, and large, the percentages displayed refer to the default batch size of 2,000 in the middle. The numbers are looking really good, but it can get even better. We've got one more thing we can enable. If we turn on native histograms with custom buckets, it gets even better. More than 50% reduction in payload size, over 70% reduction in serialization CPU time, and a nearly 90% reduction in memory allocations during serialization.
Can I add one more thing?
Yeah, sure.
This is what it is. Essentially, we convert classic histograms to native histograms with custom bucketing. So this is why we see such an improvement, and this is super epic.
Yeah, so this is the main gift of Remote Write 2.0. More native features with more structured data to help transactionality at a considerable reduction in payload size and serialization costs. Stringing turning bought us considerable headroom to add new features, and that means there's room to add even more in the future. So, what do you have to do to use it? It's pretty simple. The configuration changes are simple. You just have to provide a feature flag to let Prometheus know to use the WAL for the metadata. So it's got the storage system has the data to work with. Then, as you can see here, you just need to tell Prometheus that a specific remote write target should use the V2 protocol rather than defaulting to 1.0. Of course, it goes without saying that the target system must support the reception of Remote Write 2.0, and obviously Prometheus now accepts it, incoming Remote Write 2.0 too. As for helping adopt it, we need many of the existing tools that speak Remote Write to be able to speak the new version of the protocol. Client libraries will need to be updated if not already, and configurations options added so that systems that work in mixed environments of Remote Write 1.0 and 2.0 can know which one to speak to the target. There are also work in progress to provide test frameworks for both senders and receivers in order to make compliance checks much easier without needing to deploy or install and configure a full Prometheus instance. Other tools such as Avalanche and K6 are great for load testing and integration with your CI pipeline. And you're welcome to go digging around in the Prometheus code for the proto-buff implementation. It's there, we're not hiding it. But there's also an entry for it in the buff.build schema repository. Buff.build has tools to help you get up and running even faster, including creating Go code that implements the protocol. So, in summary, Remote Write 2.0 enables a great set of features whilst also making some significant improvements in efficiency. It is simple to configure, and if you're the owner of a third-party project or tool, we invite you to upgrade, test compatibility, and reap the benefits of the improvements. It's still experimental, so we would welcome any feedback you have, and we'd also welcome contributions and enhancements to the project. There are plenty of areas we can make further improvements. Increased increased transactionality, better, faster compression, OTLP export, the list goes on. And finally, we'd like to thank a few people who aren't up here on stage who made huge contributions to this project. Callum for the original idea, Nico, Pascalis, Tom Wilkie, Juraj, Arthur, and all of the original 1.0 authors. And so finally, we'd like to thank you for your time, and we'd like to open it up for any questions that people may have.
Thank you so much.
Awesome. Thank you, Bartek. Thank you, Alex. Yeah, questions. Right, perfect. Julius, can you do this? While I give you the speaker gifts that I've forgotten.
Well, we need that, yeah.
Speakers.
Oh, we get theirs as well, do we?
You get one of these Prometheus bottles as well, and all the other speakers. Please find the moderators afterwards to get the...
Thank you.
Cool. Thank you guys for the great presentation. You mentioned that probably in the future you can review all the other protocols like OTLP and Arrow. Just wondering if, just for fun, you test the new implementation and trying to compare with the other options, just for fun, to see if you have any benefits or not.
What implementation exactly?
Like the 2.0 remote write, if you just for fun compare it with OTLP or Arrow, or something like that.
Yeah, so we would love to, but Prometheus storage model doesn't even support certain features, so it's kind of hard. Yeah, I guess we could check, serialization encoding and compression sizes, but yeah, I don't know. We didn't for sure. We didn't include it, but yeah, I don't know. We kind of would love to. Yeah, I don't avoid fighting on compression system, because then OpenTLP has this arrow which has apples and oranges kind of problem. So we don't want to maybe highlight things, but string interning is pretty sweet, helping with things. They have of course arrow and stateful kind of protocol, which they can pull off as a better. So at the end we are in the same family, in the same kind of business. So we are innovating from a different angle, from this Prometheus adaptability angle. So it's really good to see benefits of both and kind of allow users to check to kind of choose, right?
Cool. Thank you.
Hey guys. Thanks for the talk. I have two questions. One, so the metadata that's included on the per time series, that's also going to include metric type?
Correct.
Okay, cool. And then the second question is, are there any plans to support an official client library?
Official client library? Do you mean for sending remote write?
Yeah.
We actually have it in a sense of many solutions, including OpenTelemetry collector, they literally import clients and then receivers, or handler we call it, from the remote packages in Prometheus repo. So that's our library. But maybe refer to actually versioning this properly and have a stable version, right?
Yeah. Yeah.
Yeah, that's something to consider. Yeah, I think that's a great idea.
Yeah, putting it in its own repo. And
exactly. Yeah, a separate module like OTLP has with export and ingestion. Yeah, okay. Love the idea. Thanks. Yeah.
Cool. Thanks.
Hi. If you're up to some live PR review, I have a PR implementing the ingestion of created timestamps from Prometheus Remote Write v2. Yeah. And in the code, you have a counter that I just learned is for the header partial success. So what is important? When you ingest created timestamps in Prometheus, what we do with the feature flag, we ingest that as a sample. So if we ingest a created timestamp on the remote write protocol, does that count on the reader? I don't remember the reader name, but the one that tells you how many samples you ingested.
Yeah.
Should we consider that as a regular sample, or?
Yeah. Fair point to maybe include that in some, in our specification, but I think it would be fair to really not include it, because in some way, this is to confirm what samples you received and reach into your storage. And if that storage kind of have to create fake sample to mimic some created timestamp functionality that it's not there yet, that's not part of the confirmation. So I think it would be fair to not include it. Yeah, because this is really to check for corruptions between two clients, sender and the receiver. And funny enough, there was cases in current implementation of 1.0 that those corruption could happen and you wouldn't notice, because Prometheus, for example, 1.0 handler wasn't checking content header, really. So there were things that we are super proud of this write kind of confirmation. It allows so many use cases. Yeah, thanks.
Hello, thanks for the presentation. It's interesting to know how this remote write 2 protocol is implemented in Prometheus.
Yes.
Yeah. And my question is that this string interning built into this remote write protocol looks like not so easy solution compared to just changing this compression from Snappy to some more efficient compressions such as ZSTD. Yeah. Did you try it, and what were results for this?
Do you want to?
Yeah, sure. Yeah, we tried a whole manner. We've got a whole load of benchmarking that was done, trying Z standard, trying Brotli, there's a whole load of them that we could. And what we found that just the bigger benefits were having less data before you even hit the compression side of things. If you can really thin down the bytes you want to send before you try and compress, it's worth 10 times as much as a far better compression system. So it looks a little bit complicated, but it's actually quite easy to do in practice. You basically, every time you want to use a string, you're checking if something exists in a hash table.
So essentially what I hope, I wish I had a slide for you, but we just have so much content already. Like ZCTD was adding maybe to compression ratio like, 7%, but it actually increased CPU and memory as well. So this is why it's not super obvious solution. And definitely with and without string interning, we can see that string interning helps on top of ZCTD a lot. So it's super worth it. In fact, what's amazing is that when you decode all of it, you just have more memory like in those byte structure. So I think you will be happy actually with the solution. Try it out, give us feedback, and we have in Go, we have ready symbolization helpers that literally translate symbols to your labels, and all of it is just kind of like pretty easy to use, I think, compared to maybe other advanced features that we are bringing recently. But good point. Let's address that.
Yeah, and one other point about it is we haven't closed the door on future changes to compression systems. We just found that changing that as well as changing the protocol would have been just too much of a change right now. So we can do further investigations and we can add more compression systems to 2.0, whether it's either 2.1 or something else in the future.
It's actually likely we'll add ZCTD in whatever, 2.1 or whatever, yeah. Thank you.
Yeah. So I have a question a bit related to this. In order to implement or use this protocol, and the client libraries, they need to do the string interning, right? If I understood correctly. And
yep.
Did you consider potential challenges in terms of how to implement that and how that could impact the performance? I'm thinking in like languages, I don't know, like Python or other client libraries that are not Go.
I mean, you need map. You need one data structure. You need map to kind of like get those references, to really intern those strings. So, like you can check the code of our symbol, whatever structure in Go. It's super simple. Like, so I wouldn't envision like huge problems there. And what more is that if you look on Prometheus, what we realize it like all our strings in, for example, labels, like it would use string interning. So we actually have string interning for every, labels in our Prometheus storage. So I think it allows actually more optimizations where maybe we reuse the same references or something. We have like a global string interning across the storage, the Prometheus kind of database. So yeah, there is some additional code you have to write, but it's just one mapping. It's a simple algorithm. So we hope there will be no hurdles, but give us feedback if you see any bigger problems or inefficiencies. But generally, yeah, you spend more CPU on string interning and de-interning back, but you achieve much more. You save much more for marshalling and unmarshalling kind of less work on that part.
Maybe to add to that, the remote write protocol is also meant to be sent from a Prometheus server that has already collected samples from with a different protocol onto some other endpoint. So like most of the remote write in the world is going to happen from Go code anyway. So likely you will not have to use it from your own service instance or so. Because it does kind of also expect the data to be already a little bit more pre-aggregated and coming from multiple instances and so on, right?
Yeah, you're right. On the receiving side, we might see more variety of languages, but let's be honest, it's like probably Go or C++ at this point, yeah. For efficiency reasons, or Rust.
Any others?
Another question here.
Yeah.
Here, over here, at Matthias.
Oh, hello.
Yeah, hi. You said it's experimental now, so it's pretty fresh. Do you have any rough plans when it might go into, I would say, beta or even stable? So like a year from now on, when we look at native histograms, it kind of took a while until that feature flag got removed, but surely I cannot try this in production yet. So just what we can expect.
We didn't set any specific goal, but I think we're chatting about 3 major solutions other than Prometheus adopting this, and then them being happy and actually have some usage of that, and then we can claim it. So yeah, I hope for at least Thanos, Mimir, maybe some cloud providers to give us a meaningful data. So I think it's not about time; it's about the usage. Yeah.
Okay, and you said also that with the headers you can resend data which has not been transferred correctly the first time. So is this something you have already implemented, or is this on the roadmap to be done?
That's a good question, because this is tricky. You need to know if the target is idempotent, right? So essentially, can you send? Because there is no logic right now. It would be very difficult for senders to strip those samples that we know they were confirmed and not. So if anything, this is right now possible with the protocol if the backend side is idempotent. So sender can just repeat the request even though some data was ingested. So it's up to you. Right now in Prometheus receiver, for example, we in Prometheus we kind of always, whenever we have a partial error, we always fail the whole thing and we revert, we roll back, right? But solutions for example, in Google, our Monarch metric solution, it will accept those samples. There is some logic to handle double writes, and it will be fine. So this is how you would retry. So ideally, from the protocol perspective, it's super simple, but this case can be implemented as well, yes.
Cool, thanks.
Okay. Again, thank you, Bartek. Thank you, Alex.
Thank you so much.